time that I thought of it myself. So, all right. Okay, so I do want to mention a couple of things before I start to get into the rest of Unit 2, which we're finishing up. In fact, the test is really on Unit 1 and 2. And one is that I still haven't gotten an academic integrity statement from everyone. So if you have not sent me an email promising to do your own work this semester, I will not send you the quiz. Okay? Maybe I will send an email telling people and reminding them. It could be I missed a couple, but do I know who's I'm missing? I kind of do know who's I'm missing, although I may have. I think what I'll do is later today, I'm going to send an email to everyone that I think did not send it. And I'll give everyone a heads up so that they have to send it back. So that's number one. Number two is, let's see. Yeah, I have not graded assignment 2. Well, I don't think it's due until tonight, right? Is that true? I think so.
Yeah.
Yeah, it's due tonight.
Yeah, so what I'm going to do is, okay, so I'm going to, I want to post the solutions pretty soon. Because graded assignment 2, there's a problem on the exam that's, asking similar things. And I want you to know what I expect. So I'm going to be wanting to post those solutions pretty soon. So get it in. Because once I post the solution, it's closed. I can't accept anymore. Obviously, that doesn't make sense. So yeah, so another thing is that, I think you should take this look. When I give out the exam, you should take some time to look it over, do the problems you know how to do right away. You could do those, but there's quite a few problems on it, and you're going to have to spend some time on it. And it's fine if you want to contact me. I can perhaps help you, figure out what, like if you don't understand the question, something like that. I'm sorry. Yes, somebody just asked me, when am I going to post the solutions to graded assignment 2? Obviously not before the deadline. I'll post it tomorrow, probably afternoon or something, when I give out the exam. So anyway, I'm considering having some office hours for people with questions. People who don't understand something that I'm asking about exam 1. I just think I'll probably have some on maybe Friday. And you could suggest another day, another time. But Friday afternoon is really good for me. Although I know some people work on Friday, so just let me know. But like I said, I'm pretty available. So, I would rather that you ask me something than that you cheated and copied an answer from someone else. I don't want to catch people cheating. I really don't. Anyway, so I would like you to come to me if you have questions. I can't do the test for you though, but I may be able to clarify something and point you to where you could go to figure something out. Okay, so that's what I have to say about the exam. I'm going to continue talking about water for a while. Water is so important, obviously, in our life here on Earth. And last time I talked about how water has a very large heat capacity or specific heat. It's usually called specific heat when it's expressed per gram, and heat capacity when it's expressed per mole. So I kind of throw it together and I just refer to it as a specific heat capacity. And I talked about what it means to have a large specific heat or specific heat capacity last time. If you remember, I did a comparison of adding the same amount of heat to 200 grams of iron and 200 grams of H2O. And each starts at 0 degrees C. And I add 46, something like this, 46 kilojoules or something like that. So I put a certain amount of heat into both of these, and water went from 0 degrees to 55 degrees C. That was a given. I told you it heated from 0 to 55, but we figured out that the iron would go from 0 degrees to 511 degrees. And the reason for that is that this specific heat or specific heat capacity for iron is something like 0.4. I'm going to give you the approximate because I don't have it memorized. And for water, it's 4.184. That's one I do have memorized because it's such an important number. So this is a much larger, by a factor of 10, capacity or specific heat than the iron. And what that means is that it takes that for the same amount of energy, water's temperature doesn't change. If you remember, its Q is MCS delta T. I really would love it if people would come on time so that I don't have to be doing this at 2:15. But anyway, so this was the same amount of heat that I put in, the 46 kilojoules. The mass was the same, but because water has such a high specific heat, because this was so high, this becomes a small delta T. So the CS and the delta T are multiplied together. So if one is large, the other is small. So if you have a substance with a very small specific heat and you give it a certain amount of heat, its temperature can change a lot. But substance with a very large specific heat, with that same amount of heat, its temperature will change much less. So that was how I introduced that whole thing. And then I talked about how water actually, this is a really, really high value. This is a high CS for a liquid. Anyway, so I started to talk about why water would have such a high specific heat. And when we talk about gases, and I tell you what happens when you heat up a gas. So let's start with that. If you heat a gas, what happens is that the particles move faster. And this goes along with an increase in temperature. So if all that happens is the particles move faster, then the temperature is going to go right up. But with water, if you heat water, the particles move faster. They always move faster, gas or liquid, when you heat them up. But that's not all they do, okay? If you heat water, so I would say, yes, the molecules do move faster. And that means you have an increase in the temperature. But also, remember what I said last time? Does anybody remember what I said? What does that energy go to do? It goes to disrupting those hydrogen bonds. It disturbs, it stretches them, it distorts them, it totally disrupts them. And any disruption of those hydrogen bonds, those are attractive forces, right? To sort of pull them apart a little bit, it's going to require energy, okay? So the energy also goes into doing this. And because of that, water can absorb a lot of energy. Okay, so where does the energy go? It mostly goes into disturbing hydrogen bonds. And because water has so many, it can take a lot of heat, right? So it's a heat sink in a way. You put heat in, it just takes that heat. Okay, so that's why water temperature doesn't change much. This is why water sort of resists temperature changes. Well, it doesn't, it doesn't go up as much as for other substances. And that's really a very unique property of water. Okay, and on our planet, on Earth, we have a lot of water. And so the large specific heat capacity of water, basically the oceans, tends to mitigate. Mitigate means like to lessen. It lessens the temperature variations on Earth. So that's very important in terms of understanding climate. So I would say water's large specific heat capacity, that CS number, tends to lessen the temperature changes. On Earth. And what I'm really referring to is seasonal type of changes. So if we have a coastline, let's say, here's the ocean, there's some waves, okay? So here I've got the ocean, and then I've got the land, all right? So what happens in the summer? So in summer here in Rhode Island, there's a lot of heat in the air, okay, and on the land. And so the water, the ocean, absorbs lots of heat from the land and from the air. But the temperature doesn't change that much. I mean, it changes, but it doesn't change that much, okay? The temperature doesn't change that much because water has such a high heat capacity. Okay, so what this means is that it lessens the presence of water, I should say, sort of lessens, it mitigates the seasonal temperature rise. So if it wasn't for water, the climate, the summer weather would be a lot hotter than it actually is, believe it or not. It seems like it's a very gets very hot, but it would be hotter. And the same or the opposite happens in the winter, right? So in winter, the air is cooler and the land is cooler and water is transferring heat, all right? So water releases heat because the land is cooler now. But at the same time, it doesn't cool too much. And that's also because the specific heat capacity is so high. So this also lessens the seasonal temperature drop in winter. And it's another interesting thing to think about is, have you ever been in the desert? We're so used to being here on the East Coast, but in the desert, there's no water. There's no water anywhere, okay? There's not even any water droplets in the air. There's no humidity, right? No water vapor in the air. And so what happens is you see very large temperature fluctuations from day to night. Okay, you have blaring sun during the day, very hot. At night, it's very cold. Okay, because there is no water present to mitigate these changes. So, go bring a sweater when you go to the desert, right? Yeah. So I also just want to make a case for how, if you want to understand climate and climate change, there's just so much involved. It's really not a simple thing. So to understand climate and climate change, one of the many you need to do is think about the oceans and the water vapor in the air. So climate scientists really have a lot of things that they have to look into to understand at all what's going on. So that's my little plug for trying to understand those climate people. Their models, they have to worry about a lot of things. All right, so I just want to go over a little bit a heat calculation. Oops, thought I was highlighting it, but no. Okay, so I want to just do an example for you of a type of problem where you would calculate the amount of heat that a sample of water would absorb as its temperature changes. Okay, now there's something you have to keep in mind when you do a problem like this, and I guess I'll write that here. You must keep the phase changes in mind whenever you do a heat calculation with water or any other substance, but really we're only talking about water here. Keep the phase changes in mind. So what you have to do is when you see a problem like this, you have to mentally, what happened to my pen? Oh, I see, I gotta hit that little X. God, that's crazy. You have to mentally sort of keep track of the changes. Oh, this is going to drive me crazy. Or I'm just crossing it out. Of the phase changes. So, for example, in this thing, you're given 10. You said 10 grams of ice at negative 15 degrees C is heated to 40 degrees C. Well, you have to think, okay, it's not just going to be ice at 40 degrees C, right? 40 degrees is above the melting point, obviously. It's going to be liquid water at 40 degrees C. So what you need to do is you need to break this down into steps. Yeah, this little thing is going to be with me the whole time because of some stupid Blackboard thing, but oh well. I'm going to try to ignore it, but I know it's going to drive me nuts. So what's going on? What we have to do here is we have to, I know what it is. Well, I guess I don't. Oh, no, really. Okay. All right, so you have to say, okay, it's ice from negative 15 degrees C, and keep the digit, negative 15.0, to what? When? Well, you're going to heat it to the melting point or the freezing point, which is 0 degrees C, okay? So you're going to put a certain amount of heat in, and it's going to raise the temperature. So here, the temperature goes up steadily. Once you're at the freezing point, so that's step 1, then you now are going to continue to heat it, but it's not going to increase the temperature. Right now, you're at ice at 0 degrees, but you're going to be at the freezing point this whole time, and you're going to end up with liquid water at 0 degrees. So that's step 2, is the heat that you're going to have to put in to convert the solid to the liquid. All right. And then there's a third step, and that's heating the liquid from 0 to 40 degrees C. Okay. So you could have a problem where I say, we start with ice at negative 15 degrees and you end up with the temperature being 150. Well, what's the phase of water going to be at 150?
Vapor.
It's going to be vapor. That's right. Yeah. So that means that if you're going to heat this to 150, you'd have to heat the liquid not just to 40 degrees, but what would you have to heat the liquid to? First, right? Because you have to heat the liquid to 100, right? And at 100, you would have the phase change from liquid to gas. And then you'd have to heat the gas from 100 to 150. So, you have to think of this problem in steps. All right, so let's go ahead and calculate this. I put the problem here again, but I don't think I'm going to need it. I hate that thing. I want it to disappear. All right, so I have the temperature goes up steadily, temperature of the ice. Then we're going to melt the ice, and then we're going to heat the liquid from 0 to 40. Okay, so for the steps where you're heating and the temperature is going up, you use this formula. Okay, this mass is obviously going to be the 10 grams. This specific heat is going to be the specific heat of solid water, right? Because the specific heat of the solid and the liquid and the gas are all different. And this delta T, that's the final minus the initial. So it's 0 minus 15 or 15 degrees C. Okay, so that's step one. So step one, it comes out to 316 joules, right? Because, oh, sorry, I should put in this value here. This CS is 2.09 joules per gram degree C. Okay.
Professor?
Yeah.
Sorry, I'm sorry to interrupt. What is next to H2O? I can't. So, right, like when you're writing out the formula, 10 grams times specific heat, H2O and
Solid.
okay.
Yeah. And so when you put that all together, you get 316 joules. All right, so that's step one. And now let's do step two. So step two, that's the melting of the ice. Now, what do I do there? Okay, so you'll notice if you go back to this problem that you're given by this should have been a parenthesis. This should say CS paren H2O solid. I don't know why the parentheses isn't there. And this is another important number here, and that is the heat of fusion. And remember that the heat of fusion, this should have a little 0 here. This is the heat that's absorbed when 1 mole of solid water forms liquid water. Okay, and it's given, and it is 6.02 kilojoules per mole. So this is per mole. So that means I'm going to have to take my 10 grams and convert it to moles using the grams per mole formula. And that is 0.556. Okay, so I'm going to go down here and finish that. So for step two, I'm going to have 0.556 moles times 6.02 kilojoules per mole, which gives 5.32. Nice. Oh, well. My carefree day is over already. Already, this thing is already given out on me. Oh, you can see this, so I am sharing it. So I had 0.556 moles times 6.02 kilojoules per mole. That's the heat of fusion. And that comes out to 5.32 kilojoules. So now I have heated my ice to 0 degrees. I have melted my ice at 0 degrees. And the third step is to heat the liquid from 0 degrees C to 40 degrees C. I'm trying to use the same sig figs in the problem. So again, now, so I guess I should say, by the way, this melt ice, what you do, and this is the phase change part. I should have said this. So you take the number of moles times the delta H0. It's for fusion, which if you were vaporizing, oh, hold on, I'll check that in a minute. If you were vaporizing, you'd use the heat of vaporization, which is per mole. So this is what you use for the phase changes. You take the moles times the delta H for that particular phase change process. Yeah, no, that's not right. This was the total at the end. I copied it wrong. And this comes out to, yeah, thank you, 3.34. Sorry. And finally, this is again MCS delta T, except this CS is for the liquid. Okay, and it's different, and it's a different number given in the problem. And so it's the mass 10, 4.18 joules per gram degrees C. This is CS of the liquid for water. And now we have 40 minus 0. So this is also 40.0. And this comes out to 1674 joules, which is only 3 sig figs, right? So I'm going to write it in kilojoules. So I basically divided it by 1,000, because notice I have kilojoules here, and I'm going to want to add these up. If I go back to number 1, I have it also a number in joules, which is 0.316 kilojoules. So now that everything is in kilojoules, I can add them up. And that was the number I gave you before, unfortunately. So 0.316 plus 3.34 plus 1.67, that's 5.32 kilojoules. So that is the total answer, the total amount of heat. But, you know, if you start with ice and you're going to a temperature of 40, you're going to end up as liquid, and you've got to take care of that phase change. If you start at 25 and you're going to 150, you're going to have to get to the boiling point and have a phase change. So you got to be careful in problems like this, that you break it down into the right number of steps so that you can add up all the different contributions to the heat. Does anyone have a question about that? Okay, moving right along. To continue, I have more things to say about water.
Professor?
Yes.
So we take all these three steps only when we have phase change, right?
Well, look, this was for the phase change. This was for going, this first one was for heating the ice. This was for the phase change from solid to liquid, and this was heating the liquid. So, you know, depending on what the temperature is, you know, if I start at 50 degrees, that's not going to be ice, right? That's liquid water.
Yeah.
Boiling point's 100. So if I start at 50 and end up at 150, I got to go from 50 to 100. So that's heating the liquid. Then I got to vaporize the liquid. Then I got to heat the vapor. Those would be the 3 steps you'd have to do. Okay.
Oh, okay.
All right.
Thank you.
Sure. Anyway, so the large CS, specific heat of water, is one, you know, pretty unique property. But there are others, okay? Water is an amazing substance, and I'm going to dedicate a few minutes today to talk about water, okay? So I want to show you the structure of ice. So this is basically solid water, okay? And the hydrogen bonding is really very important there. In fact, well, let me show you what it looks like, okay? So I have some pictures here. God, where did I put them? Oh, here's one. Okay, so let's go a little closer on this. So this is like a two-dimensional view. This is like a top view of ice crystals. I'm going to show you the 3D in a minute, but I wanted to spend a little time on this first. So you could see, here's my water molecules, right? I've got H2O over here, and then I got another H2O over here. And then, you know, all of these what are these red dotted lines? The red dotted lines are the hydrogen bonds, okay? The intermolecular forces. So these red lines here are the hydrogen bonds, intermolecular forces. Okay, so what happens in ice is really unusual. These attractions, these intermolecular forces, this hydrogen bonding between water molecules stabilizes water, okay? And so to get the maximum number of these stabilizing hydrogen bonds in the solid, it leads to this hexagonal structure that you see here. And you could see it even better here. This is like a blow up of one of these hexagonal structures. And you could see that every water molecule is forming hydrogen bonds with many of its neighbors. And so the hydrogen bonds are actually not shown in this picture, but basically in all of these, many of these diagrams, red always represents oxygen and either yellow or white represents hydrogen. So this would be a hydrogen bond. This is another hydrogen bond. This is another hydrogen bond, another, okay? So you could see that with this hexagonal structure, you get a real lot of hydrogen bonds. And what that actually does, this amazing thing, what it actually does is it pushes the water molecules to be a little further apart in the solid to make room for all those hydrogen bonds than it is in the liquid, which is incredible. It's one of the few solids that actually is less dense than the liquid. So I'm going to write some of this down. So the hydrogen bonds lead to this hexagonal structure. And to maximize the number of these stabilizing hydrogen bonds in the solid, the water molecules are actually further apart than in the liquid. So, and anyway, this is extremely unusual. Most of the time, the solid is more dense, okay? So it's very unusual. The solid water is less dense than liquid. And usually it's the other way around. So this is very unusual. Okay, so that's why, right? That's why your ice cubes float. And why icebergs float, of course, same thing. Okay, it's because the liquid is actually more dense. Okay, so now I'm going to show you some three-dimensional pictures of water. Okay, so let's take a look at this. All right, so what I want you to see is that, like this atom here, this is actually oxygen. I'm going to make it red because oxygen is almost always depicted as red. Here, hydrogen is depicted as black. I don't know why, it just is. So this is the oxygen, the O, and these are hydrogens. And now what are these things then? You know, what is this thing and this thing, right? And this thing. They're all going from oxygen on one molecule to hydrogen on another molecule. So what are those guys? What would you call them? Maybe someone wrote it in the chat. No, nobody wrote it. Come on, what are they called? Those are your hydrogen bonds. So I'm going to write that. In fact, all the straight lines here are hydrogen bonds, okay? And it's keeping these in place in the ice, all right? So when you look at this closely, you blow this up, you can say, oh my gosh, look at that. What is that? That's actually a tetrahedral structure here. I could draw a little tetrahedron here. Okay, that geometric figure. So you end up with this tetrahedral structure in ice. And basically every oxygen is surrounded, has this tetrahedron of hydrogen bonds attaching it or holding it to other water molecules. And this is a top view, but it's kind of shifted. So you could see what the hexagons look like underneath. And so anyway, water is a pretty fascinating substance. And of course, the important consequence of all this is that, to have room for all of those hydrogen bonds, you end up with ice that is actually less dense. It's more compacted than the liquid. So that's a very unusual property of water. Okay. So let me show you something else that is truly amazing about water. And that is, this diagram, this looks like nothing. It's just a table with some silly figures in it. But let's take a look, okay? We have molar mass here, okay? And these are all very small molecules. So what I have here is the boiling points of some small molecules. And most of them, except for ammonia, have higher boiling points than water. But still, I'm sorry, higher molar masses than water. But these are all very small molecules. Look, 2 N's, CH4, very small. And look at these boiling points. Nitrogen, negative 196 degrees C. Really cold. That is extremely low boiling. What does that tell you about nitrogen? Why is nitrogen so low boiling? It has to do with intermolecular forces. What does it tell you about nitrogen's intermolecular forces?
It's easy to break them apart.
Yeah. First of all, it has only dispersion forces, and then it has a very low molar mass. So it's easy to break them apart. I'm not talking about breaking apart the nitrogens. It's easy to break apart the intermolecular forces that hold two nitrogen molecules together. Okay, so look at that low boiling point. Water has an even lower molar mass, and yet its boiling point is 100 degrees C. Those hydrogen bonds are responsible for a lot. And of all of these, only water is the only one of these small molecules that has a BP that is greater than that's greater than room temperature. Remember, room temperature is 25 degrees C. So these are all gases at room temperature except water. And water isn't anywhere near a gas at room temperature. You have to heat water up to 100 degrees to get it to go into the gas phase. And this is all because of those strong intermolecular forces of hydrogen bonding. So it's a really, hydrogen bonding is a really big deal. So I hope that you can, appreciate that, with this chart here. Water is really unique. And I guess we're all glad to have it, or we really wouldn't be here. Okay, so that's what I have to say about liquids. I have only a little bit to say about solids in this course. And I'm going to tell you about the different crystalline solids that exist in nature, at least for us people in Chem 103 or 104 who are trying to understand sort of on a simple level. So I'm going to talk about crystalline solids. And I'll go through the 4 types, but I'm not going to I'm just going to show you examples, and I'll put those examples in context of types. Okay, so when I do this unit, very often I will spend time looking at, well, first of all, crystalline solids. What makes them crystalline is that there is a repeating pattern. We say that there is a repeating unit. It's kind of like crystalline solids are like wallpaper, you know, even high quality wallpaper. You could look at it for a long time, you find the repeating pattern, okay? It might be this big or it might be this big. It might be hard to find, but there's always a repeating pattern. In solids, we say that there is a repeating unit, and we call it a unit cell. And this is the smallest repeating unit in the crystal. And a lot of times when I teach this course, I ask students to learn how to figure out the formula from a unit cell. But we're not going to do that this year, so no formulas from the unit cell this year. Okay, so we're going to skip that. But I'm going to show you some unit cells. Oh, by the way, because of this, we're going to skip activity 9, number 1 and number 2A. So we won't be doing that in 2021. So here is a unit cell. So this is the smallest repeating unit of a sodium chloride crystal. So this is an NaCl unit cell. I'm going to cross this out because we're not dealing with formulas this time around. So this is NaCl. This is one type of crystalline solid, which is called, so this is an ionic solid. This is the type 1. I don't call it type 1, but this is 1, you know, crystalline solid type is ionic, okay? And that means that each of these particles are ions. So this is showing one that's just NaCl, right? How do I know which is the Na and which is the Cl? Well, if you look on the periodic table, when you have sodium has an electron, has 11 electrons, okay? It's configuration, which we haven't, talked about in forever. But that is its electron configuration, 6, 7, 8, 9, 10, 11. So when it becomes a sodium ion, it gives up this 1 electron, okay? And it ends up as that, and that is the electron configuration of neon, okay? Now, the chlorine, when it becomes chloride, chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. So it's going to gain an electron. It becomes Cl minus. So it's going to end up as 3p6, or it's going to end up being the configuration of argon. All right. Argon is much bigger than neon. It's in the next row down. So this is larger. So that would mean that the blue is the chloride, and the funny color green here is the sodium ion, okay? So first of all, in an ionic solid, like I said, the particles are ions, okay? What you see here are the negative charged ions surrounded by positively charged ions. So what's holding this together? What's holding an ionic crystal together. What do we call those bonds between the sodium and the chloride? All of these things here.
Can you scroll up just a little bit, please, for like 1 second?
Like that?
Thank you. Yep, that's all I need. Thank you.
Yeah, so all of these gray lines here, every single one of them, these are all ionic bonds. Now, ionic bonds are strong bonds, okay? What's holding them together is ionic bonds. And an ionic bond is simply the attraction of unlike charges. And these are strong attractions. Okay, so anyway, they're pretty solidly held together. Now, can you see in any individual molecules here? Now, when I teach Chem 103, I'm very careful. When I write the formula NaCl, I never refer to it as being a molecule because it isn't. Does anybody remember what their chemistry teacher would refer to that as? What do we call it? We say one what of NaCl. You say 1 unit of every NaCl. We call it a formula unit. Okay, and that's because it's not a molecule, because there are no molecules in this picture. All right, there are no molecules in this repeating unit here. You do not see clusters of atoms together. You just see repeating spheres, or some, I'll show you another one that's not necessarily always that way, but there are no groups of atoms clustered together. So there are no molecules per se. And that's pretty typical of an ion. That's what ionic compound does not have molecules. So what can I say about ionic compounds? So let me give you some facts about it. I've said some things already. Let's sort of put it together. Okay. This is one type of crystalline solid. It's arrays of plus and minus charged ions. Okay. Sometimes there can be polyatomic ions. And I have an example of that here. Unfortunately, I didn't put this in the slides, but that's, yeah, I'm just showing it to you now. So this yellow is a sulfur. And then, you know, we have these, unfortunately, we have red, and then we have this copper colored. So this is a copper here. And these are 4 oxygens. This is actually a sulfate. Okay, so this is a sulfate, but still, even when you have an ionic compound with polyatomic ions, you still have arrays of positive and negatively charged. In this case, you have a group that's negatively charged, but there are no molecules. There are no clusters. Okay, it just kind of goes on and on. All right. So what would be true? So there are no individual molecules. So what would you think would be true for ionic compounds in terms of the melting point? So what would you have to do to melt an ionic compound? So what does melting involve in a compound like this? Well, it involves sort of loosening the attractions between the sodiums and the chlorides. So to melt an ionic compound, to go from a rigid solid to when the particles are more free flowing in the liquid, you've got to break ionic bonds. And this is not easy. So what would you say about the melting points of ionic compounds? Do you expect them to be high or low?
High.
High. They will have high melting points. Another thing I could say is if you have an ionic compound like NaCl, where you have a +1 and a -1, and you want to compare that to, say, magnesium oxide, where you have +2 and -2. Which of these do you think, and these are about the same size, which would have a higher melting point? What do you think? Which would have a stronger bond? What happens to the attraction when the charges get bigger? Here you have greater charges, greater magnitude, or greater strength of charges. So is it going to be easier or harder to pull those apart?
Harder.
Yeah. So these are harder to pull apart. And so you'd have a higher melting point. Okay, so different things, charges matter. Okay, well, what else do we know? What else can we?
Professor,
Sorry?
I'm sorry. So you're saying based on the charge is how you'll know if it's harder to pull apart or not?
I'm saying that all ionic compounds will have fairly high melting points, but one that has doubly positive and doubly negative would have a higher melting point than one that was just 1+ and 1-.
Got it. Okay, thank you.
Okay, another thing is, what about conductivity? That's another property. Conductivity. So conductivity has to do with the movement of charges, movement of charge. Okay. So something that, and I'm talking about of electricity. So I'm talking about electrical conductivity. Has to do with how easy will charges be moving around in an ionic compound. And the solid, so a solid ionic compound, can the charges move? No, they're stuck in place, plus, minus, you know, on all, going in all different directions. So they're stuck in place. But what if I melt the solid? So what if I make a liquid out of it? Okay. Get rid of this. So a solid ionic compound is stuck in place, does not conduct. So even though it has charges, those charges are immobile. But if you melt the solid, now the charges can move. So the liquid conducts. So that's pretty unusual. Ionic compound, solid, doesn't conduct. If you take 2 electrodes and you attach it to a light bulb and you have a battery in there, so, and if you stick those two, if you touch the 2 electrodes to each other, you've completed the circuit, the light bulb goes up. You put them in a thing of salt, NaCl, you think, oh, it's charged. Maybe the light bulb will go on, nothing. But if you were to melt that NaCl, which would be pretty damn hot, and you wouldn't want to be too near it, then it would conduct and the light bulb would go on, all right? Okay, what can I say about hardness? Because that is one property of these crystalline substances. So let's see. So I was talking about melting point up here. I have a nice chart, by the way, at the end that I'll show you that puts it all together. So melting point, electrical conductivity, hardness. Well, it's pretty hard because those bonds are strong. the ionic bonds that are holding them together, but they're not always, they have these something called crystal planes, which are like planes of weakness. So it can crack along these crystal planes. So it's not easy to tell if something is ionic by knowing if it's hard or not. And so that's all I'm going to say about that. Okay, so let's look at now. Here is another diagram, another picture. Oops, gotta get this out of the way now. Okay, so here I have gallium arsenide. This is the arsenic part, and these blue ones are the gallium, okay? And this is also like a repeating unit. It doesn't look like there's any molecules here, right? I don't see clusters. So here is, it looks like no clusters. So no molecules. But I'm going to tell you that this looks pretty similar to the last one, but it's actually a different kind of crystalline substance. This is called gallium arsenide, and it is a covalent network solid. So this is a second type of crystalline solid that I'm going to tell you about. Covalent network solid. Okay, so what that implies is that the atoms here, so the atoms in a covalent network solid are bound by covalent bonds. So all of these things here, these are all covalent bonds. And covalent bonds, as you know, are also very strong. Okay, so if you were going to melt gallium arsenide, you'd have to break up covalent bonds. Okay, but first, before I talk about that, we don't worry about the phone. I want to show you that covalent network solids tend to be involving elements in this part of the periodic table, kind of like over here. So I would say there's a lot of metalloids involved. In fact, if I blow this up, you could see that gallium is very close to being something near a metalloid, and arsenic is a metalloid. So it's very typical of covalent network solids to consist of atoms in this part of the periodic table. So metalloids and nearby elements. Okay. Atoms are bound by covalent bonds. What does that mean as far as melting point? Well, you have to break covalent bonds in order to melt this substance, okay? So you need to break covalent bonds to melt. And that takes a lot of energy. So these guys have really high melting points. And another thing is, if the melting point is high, then what would you say about this enthalpy of fusion, which is the heat needed to melt? These two things go together. If the melting point is high, the heat of fusion is high. You need a lot of energy to melt this type of substance. Gallium arsenide, for example, has a melting point of 1238 degrees C. So these are hugely high. Some of them are even in the 2000s. I mean, they're kind of amazing. What about the hardness? Well, these are really the hardest substances that we know. Diamond is a covalent network. I'm going to show you a picture of it. So these are very hard. And that's because to break up, you have to break covalent bonds. Okay. So here's a picture of diamond and graphite. These are all of the atoms here. Every single atom in this picture is carbon. Okay, so this is carbon diamond, and this is carbon graphite. Okay, and the diamond, look at this. Here is a carbon. It is covalently bonded to 4 others in a tetrahedral shape. Okay, so every single carbon in diamond is bonded to 4 other carbons by 4 covalent bonds. So this is extremely strong, and this makes diamond extremely hard because of all these very strong covalent bonds. Now, graphite, anybody, where do you see graphite? Graphite is what's in pencils. Okay, graphite, it has actually like layers. You can see here that you have like here's one layer and another layer and another layer. Okay, so within a layer, these are covalent bonds and are very strong. But between the layers, these are only intermolecular forces, and they are very weak or relatively weak. So what happens with the reason why your pencil breaks all the time is because of this weakness of the attraction between the layers. So within the layers, you've got these strong covalent bonds, but between them, you have weak bonds. So hardness differs from graphite and diamond, but the hardest substances that we know are covalent network. So there's some pretty awesome materials in this group.
Professor, before you move on, I'm just curious. So that blue image, that's a covalent network, and in between that is the intermolecular force, which is the weak part, which causes the things to break, is what you're saying?
Which is, yeah, that's the weakest link. Okay.
In a covalent network solid.
Well, it's in this particular covalent network solid. Most covalent network solids have just covalent bonds.
Okay.
Graphite is kind of exceptional.
Okay, so you're saying graphite's exceptional because of the weak bond.
It has sheets.
Okay.
A weak intermolecular forces between them. It's just really an interesting example.
Okay, thank you.
But most covalent network solids are very hard. They have very high melting points. And there are many of them. Okay, so they are either insulators, so either they don't conduct electricity, or they are semiconductors. So they're very important in the semiconductor industry. So for us, if I say semiconductor, that means it's probably a covalent network solid. You can pretty much say that for sure. So that's a clue. If I ask you, something is a semiconductor, it melts at 1500 degrees C. What type of compound is it? You say, oh, it's a covalent network, because that's all we know about in Chem 104. So that's an important property of them. So basically for covalent network, we've got very hard, very high melting points, and they can be semiconductors. So these are 3 important things. And that's the second type. The third type is a type that we're very familiar with. And those are molecular compounds, or molecular, I mean, they could be liquids as well, but we're talking about molecular solids here. Okay, so this is like sucrose is a molecular solid, that we're very familiar with. But let me show you a couple of pictures. So here, Okay, so if you look on the left here, this is actually crystalline carbon dioxide. So this is solid CO2. CO2 is definitely a molecular compound. But look at this. If you look at this repeating unit and you compare it in your mind to this one, right? This one here. Here you do not see individual molecules, but over here you can very clearly see that you have individual molecules. You have clusters of atoms, and that's what allows you to figure out by looking that this is indeed a molecular solid. So they have individual molecules, clusters of atoms. And over here, I have a much larger molecule in this particular compound with the very long name. Look at that name. Try saying that 3 times fast. Methyl. 2777 trimethyl 4-phenyl 5-oxo 1,4,5,6,7,8 hexahydroquinoline 3-carboxylate crystal. Pretty good, eh? Anyway, so you can tell right away by looking at these that these are indeed molecules. So this is molecular as well. And if you look closely, there we go, closely, you could see that in this diagram, there are some dotted lines. Now, sometimes you see dotted lines in a picture like this, but a lot of times they just leave them out. And those dotted lines are intermolecular forces. So what's holding these crystals together, what's holding these particles together in the crystal is not strong ionic bonds. It is not strong covalent bonds. What's holding them together are pretty weak intermolecular forces, okay? So that's the big deal here. How are these molecules held together? And that's by intermolecular forces. So how do you think the melting point of a molecular compound would compare to that of an ionic compound?
Is it a lot lower?
Much lower. Basically, the sort of rule of thumb, although it's not always true, and I found one today when I looked it up, is that they're generally less than around 200 degrees C for molecular compounds, for the melting points. Okay, so if you see a melting point of under 200 or under, you say that's, well, it's not, it could be metallic. Metallic is all over the place. That's the one I have to do next. But there are other things that would let you figure out if it was metallic. So basically under 200, and that's because of the weaker intermolecular forces. Much weaker than ionic or covalent bonds. So anyway, so the melting point of molecular compounds are generally less than 200. For ionic or covalent network, it's generally greater than 200 degrees C. So molecular compounds have, what the heck is, something else about molecular compounds. So most of the compounds with hydrogen are molecular compounds, because if you have a covalent network compound, you have to be able to attach a hydrogen to 2 different things, and hydrogen can't form 2 bonds. So you won't see hydrogen in a covalent network compound. And in an ionic compound, you might see hydrogen, but it would be, say, in ammonia, NH4+. It would be as part of a polyatomic ion. So molecular compounds can contain hydrogen, covalent network can't. And that's sometimes a good way to figure out whether something's molecular or not. Anyway, what about the hardness of molecular compounds? Well, you know, hardness has to do with the strength of those bonds. So molecular compounds are not hard at all, are very brittle, not hard at all, not hard to break. Conductivity, here's another interesting one. Well, you know, you have individual molecules, right? Well, all the electrons, they stay with their individual molecules. Electrons do not move from molecule to molecule, unless they're undergoing a chemical reaction, not just the pure compound. And so they're lousy conductors. So they are basically insulators. That's the opposite of a conductor. They cannot conduct electricity. They really don't conduct heat very well either. All right, and then let's see, there's a fourth type of crystalline solid that we study in this class, and that is the metallic solid. So metals, basically, that's what I mean by metallic. So So here is a picture. Hold on a minute. What happened there? I shouldn't have messed with it. All right, so this is just an example of different metals. So one thing you can see right away, if you look at a unit cell for a metal, metallic, is they're all the same particle, okay? So, you know, all the atoms are the same. In a metal. So if you see a picture and all the particles look like they're the same, that could be metallic. It could also be covalent network. So you'd have to look at some other things to figure it out. One thing that I could say about metals is that their melting points will not tell you what they are. The melting points are all over the place. And that's because metallic bonds are very variable in their strength. Oh, but something I want to tell you that's very important, the most important thing I should have said already, is that where these positions are, where these are, is where the nuclei are. So I want to say that the nuclei are fixed in place, but the electrons are free to move around. And that's why metallic compounds are good conductors. Talking about solids, are good conductors of electricity. And they're also good conductors of heat generally. Okay, so they're good conductors. They're all the same atom. Melting points are all over the place. So here's mercury.
Sorry. Did you say? What about what makes them the melting points all over the place?
Oh, they just don't worry about it. They just are. I said that it's because the metallic bonds are different in strength, but yeah, it's just very vague. I don't know.
Okay.
The truth, I really don't know. Mercury, though, I know melts at -39 degrees C. That's very low. Obviously, it's below the freezing point of water. Tungsten melts, listen to at 3,422 degrees C. So it's just hugely variable. So you won't be able to tell if something is a metal based on its melting point. But there are certain properties of metals that we all know from the metals that we deal with, like aluminum foil, right? And things like that. And that is that metals are generally soft. Okay, they are malleable. Malleable means they can be pounded into sheets like aluminum foil or gold foil. In fact, if we were in the classroom, I would show you some examples. I actually have a sample of actual tin foil, which is not what we call it, tin foil, but it's really aluminum foil, but they used to make it out of tin. They're very malleable. They can pound them into sheets. They're very ductile. Ductile means pull into wires. Like copper wires, etc. You know, one reason they made pipes out of lead was very easy to mold them. So they're definitely quite soft. And they have these properties. You won't see me telling you that any other like molecular compounds are not malleable. They'll just break apart. Covalent network, well, you can't even pound them. They're too hard generally. And ionic, no, you're not going to make your wires out of sodium chloride. So putting this all together, I have a nice chart here. Okay, so here I have the 4 different types that I've talked about. And here I have the different properties, melting point. I want to add to this. So molecular compounds have weak intermolecular forces holding them together. They have low melting points, less than 200. They have smaller heats of fusion. Okay, it takes less energy to melt them compared to ionic with strong ionic bonds, high melting points, larger delta H of fusions. Okay. Here I'm not going to say because it's very variable, but here again we would have large a heat of fusion. Takes a lot of energy to melt. For hardness, molecular, not hard at all. They crumble extremely easily. Ionic, not so great because they have these crystal planes that that cause some breakage, but they're harder. You can't break the ionic bonds in them easily, but there are other places you can. But metals are like extremely soft and pliable, malleable and ductile. And covalent networks, really the hardest substances known, like diamonds, carbon graphite, and other things like silicon carbide. You hear carborundum, I think that's what that is. Anyway, so, and conductivity, we have some interesting things here. You know, molecular compounds do not conduct because the electrons belong to individual molecules. Ionic compounds, you might think, oh, they'd be great conductors. They're made of ions, but the ions are stuck in place. So they really can't conduct in the solid, but the liquid phase, they do conduct electricity. So that's an interesting fact. In metals, the electrons are free to move around. It's the nuclei that are fixed, and that leads to great conductors. And I did have some slides that I'm not going to cover that deal with the orbitals and metals and in semiconductors, and I'm just skipping that. It's too much. And covalent network, semiconductors fall into this category. So they're either going to be slight conductors of electricity, somewhat conductive, or insulators, but they are not conductors. So anyway, those are the 4 basic types of crystalline solids. I think it's interesting to know some things about these. So I always go over this in this unit. There is an activity. This one has to do with finding the formula. So we are not doing this. We're going to skip this. This one, the A, has to do with finding the formula. So we're not going to do that. It's not as easy as it looks. That's why I'm skipping it. It's not really worth it. So I'm just not going to cover it. What about, so if I tell you that this compound, so if I tell you this compound is either ionic or molecular, which is it? So you look at that and
Ionic.
yes, it's definitely ionic because there are no individual molecules. If I didn't tell you that it could be ionic, what else could it be? Could it be molecular? No. Could it be metallic? Why couldn't it be metallic? What is in a metal, you have all the same atom, and these are not all the same atom. But what about covalent network? Could it be covalent network? If you didn't know, you'd say, yes, it could be covalent network. If I didn't tell you that it was ionic or molecular, then you could say, oh, it could be covalent network, possible. But if I tell you that it's either ionic or molecular, it has to be ionic. And would you expect the melting point of this compound to be greater than 200 degrees or less than 200 degrees? So, we've pretty much addressed this, right? Because it's not molecular. It's not metallic, which means we don't know what its melting point would be. So it's got to be ionic or a covalent network. And so it would be greater than 200 degrees because those things have relatively high, very high melting points. Okay. Now, what about this one? So just read what it says here. What's the most important and obvious difference between the compound shown here and the one for the previous problem? So what's the big difference between the appearance of these two? What have we got here that we don't have here? What's here but not here? Ah, somebody answered it, yes. Molecules. These are individual molecules, clusters of atoms, big clusters. So this is molecular compound. Okay. And then I have this activity 10. Okay, and this sort of speaks to the kind of thing I've been alluding to, like how do you distinguish these things from each other? So what I have is a list of descriptions. So these are all descriptions of different compounds, and these are the compounds that there could possibly be, okay? And so how do you put the description with the substance? All right, so let's think about this. All right, take a look at this. There are some clues that you should be able to figure out right away. And part of it starts with thinking about which categories do these different compounds belong to? Like LiCl, what type of compound is LiCl? What type of solid is ionic? Is it molecular? Is it covalent network, or is it metallic? Lithium chloride, ionic, that's right. What about lead, Pb? It's a metal, right? Nothing else. Just,
Yeah.
yeah. What about CaO? Anybody? Take a look at the periodic table. Let the periodic table help you, okay? Calcium is over here. O is over here. Okay. Calcium is a metal or non-metal? Come on. Somebody must know the answer. It's a metal, right? Oxygen is a non-metal. So you have a metal and a non-metal. Now, if you had, it's not metallic because it's not just one metal. Calcium oxide is not going to be molecular. Molecular compounds are basically non-metals with each other, except there's also hydrogen involved. Covalent network is usually this part of the periodic table. So that's got to be ionic. So you can classify it as ionic. What about silicon? Oh, silicon is over here in a very special part of the periodic table. It is a metalloid. And what type of compound consists of a lot of metalloids or often has metalloids? What do you think? Covalent network. Metalloids are very commonly part of, when you look at that periodic table and you look at this area here, a lot of covalent network compounds. Of course, non-metal, of course you could get molecular compounds there as well, but they often contain hydrogen, which is kind of a clue that it can't be covalent network. So, and which brings me to CHI3. So these are all, okay, so it's non-metals and hydrogen. Hydrogen kind of excludes it from being covalent network because you can't attach a hydrogen to two other things with covalent bonds. So you pretty much have to say this is going to be molecular, right? You have no metals, so it's not going to be metallic. It's not going to be ionic. You need a metal or ammonium for ionic, okay? So then if you think about the type of compound and then you try to categorize, what is the clue that is given here that tells you really what type of compound it is or type of solid it is? So it's got a pretty high melting point, right? What else?
The semiconductor.
Yeah, that's a dead giveaway that this is going to be covalent network. And so then you look back at your list here and you say, oh, it's got to be silicon because there is no other covalent network compound there, right? What about this one here? What is the key here that's going to give it away, or a couple of keys?
Malleable solid.
Malleable, conducts electricity. What do those two point to? What type of solid? Metallic, molecular, covalent network, or ionic? Malleable, only metallic. Okay, those other things are too hard. Or too brittle. You can't pound a brittle compound, which is like molecular compounds are very brittle. You can't pound them either. So they're either, okay. What about here? What about C? What is the clue here?
That the liquid can conduct electricity.
Yes. So what does that mean? The solid can't, but the liquid can. So what type of compound is that?
Ionic.
Right. So that's ionic. Well, we have two that are ionic, right? That we have LiCl and CaO, right? So we wouldn't know which one to pick right away. But if you go down here to E, this also says So this is also ionic. But then we can compare the melting points. So which is going to be, we have CaO and LiCl, I think. Which is which? We have C and E. Which would have the lower melting point? Yeah, Ca compound would have the higher melting point. And that's because if you look on the periodic table is very helpful here. Here's calcium, right? It's in the second group. It's going to have a +2 charge. O is going to have a -2 charge because it takes 1, 2 to get the complete shell. Okay, so CaO will have +2 and -2, whereas LiCl is +1 and -1. So you can sort of tell by looking at what the charges would be and where it is on the periodic table tells you that. So this is going to be a harder to break these ionic bonds. Than for LiCl, which is +1 and -1. That makes sense? And finally, we have a soft yellow non-conducting solid, characteristic odor and a melting point of 120. Okay, it's soft. It has a melting point less than 120. So it's probably a molecular, it's non-conducting, it's not a semiconductor. And so that would be this guy, the CHI3. This is molecular. And the hydrogen really does help give that away because the only way you could have hydrogen in an ionic compound is if you had like ammonium chloride. You had ammonium or something like that, polyatomic ion. Otherwise, a hydrogen can't be a covalent network. It's not going to be metallic. So it's pretty much going to be molecular. And it makes sense because the melting point here is less than 120 and it's non-conducting. So that makes this molecular. Okay. So that's the kind of thing. All right. I have a few minutes left. And I wanted to just, I wanted to show you I just want to talk a little bit about boiling points again, because this is important. And there's a question on the exam about this. So I want to make sure that, you have a good understanding of this. So supposing I was comparing these two compounds and I wanted to figure out which has a higher boiling point. And right now I'm only talking about these two, the first two here, okay? So what would you do to figure this out? What would you think about? What would you notice? So do you notice anything about the compound on the left that would, tell you something about whether it has a high or a low boiling point compared to the other one?
It has a hydrogen bond.
Well, it doesn't have a hydrogen bond. It can form hydrogen, it has the ability to form hydrogen bonds. So this can form hydrogen bonds. And this cannot. That's very important. But what does this one have, though? What is its, what type of, so this is, of course, going to have dispersion forces, as is this. But what else can this second one do? What else can this one here? What else does it have? Does it have a dipole? You should think about that.
It does.
Yeah, because this is polar here. this, you have an arrow here and you have an arrow here, which means that you have a net dipole pointing to the left, okay? So you have a dipole. So it has dipole-dipole forces. So to be complete about this, you really should compare their molar masses as well. So I'm going to give you their molar mass here is 60 grams per mole. And this guy is 74 grams per mole. So which do you think would have the higher boiling point? And is there any confusion here? Is there any conflict? Is there any, you know, what do you think?
The one on the left would?
Would have the higher boiling point? Yes. This one indeed has the higher boiling point. Why? Because it can form hydrogen bonds. So even though it has a lower molar mass than this one, that is not enough to make up for the lack of hydrogen bonds for the one on the right. And I'm going to tell you the one on the left has a boiling point of 98 degrees C, and the one on the right, oh wait, did I get that right? Yeah, the one on the right has a boiling point of 35 degrees C. So it's just any hydrogen bonding is really very, very, very important. Okay, even though this has a higher molar mass, it has greater dispersion forces. 14 grams per mole of dispersion force isn't enough to overrule hydrogen bonding. Okay.
Professor?
Sorry.
Yeah, I have a question.
Yeah.
So if it couldn't form hydrogen bonds and the rest was the same.
Okay,
So
let's answer that question, right? So
yeah, the boiling point, the other one would have
well, it's hard to answer that question, right? If I put a carbon in here, you mean? Well, look, let's look down here.
Oh, okay, all right.
Okay, I was going to get to this, but like this one is 72 grams per mole. This is 58. All right, so if we look back here, this has CCCO, so there's like 4 things, right? Oxygen is only 4 units more than carbon, so it's got 4 big atoms there. This one has 4 here, and this is 58 grams per mole. So these are similar, right? This is 60, this is 58. That's not very far apart. That answers your question, right? Because this is 0 degrees C. So this is a much lower boiling point. It has the same molar mass as this one, but it's got a much lower boiling point. Does that answer your question?
Yeah, I get it. Thank you. That was my question.
Yeah, so, okay, so now let's take a look at these 3 here. And I'm going to put down their molar masses here for you. It's very important to know the molar mass. 46, 65-ish, and 58 for these 3. Let's look at these 3 now. So this has a lower molar mass, but it has the ability to form hydrogen bonds. This one is almost 20 grams per mole greater, but it doesn't have the ability to form hydrogen bonds. It has a dipole. Okay, and so what about the boiling points here? Well, I told you, hydrogen bonds are the most important.
So that says that has higher boiling point.
Right, the boiling point of this compound is 78.2 degrees C. The boiling point of this compound is 12.3 degrees C. And now what about this one? This has an intermediate molar mass, but it has a stronger dipole here. And it has an intermediate boiling point, 56. So if you compare these 2, it's easy to see that despite the lower molar mass, right? It has a higher boiling point because it can form hydrogen bonds, okay? When you compare these two, you could see that they have similar molar masses, not that different, but this has a stronger dipole, okay? So I guess my point is that with hydrogen bonding, like really all bets are off. It's going to win. It's going to have the higher boiling point. Now look at this. Suppose I compare this molecule to these two here, right? I'm comparing it to, these are similar molar masses, okay? But this doesn't have the ability to, no hydrogen bonding and no dipole either. And you could see that this 0 degrees is lower than all of these three, lower than each of these, okay? And way, way lower than this one, which has even a smaller mass. So hydrogen bonding is extremely important, but molar masses also are important. And I could actually see that by looking at this one. This is a larger, also no dipole, but its boiling point is 36 degrees C. So, you know, it does make a difference. And sometimes it's actually hard. It's actually hard to explain. Like this guy here, 74 grams per mole with a little dipole boils at 35, whereas this one, no dipole, 72 boils at 36. So you might think, well, why doesn't this have a higher boiling point than this one? They have almost the same molar mass, and that one has a dipole. Well, that's the one you won't see on the test. You know what I mean? I'm not going to ask you to compare two things that you won't be able to figure out based on the information. So yeah, I'm just saying there's a bit of a, you have to understand there's a lot of gray areas in this. But yeah, but you really can get a good idea by looking at the hydrogen bonding and thinking about the molar masses. Yeah.
Like, you may have said this before, but like, where are the boiling point numbers coming from?
I looked them up. What do you mean?
Oh, you looked them up. Okay.
Yeah, no, you can't. No, you can't. You can't predict what they're going to be. You can explain. Well, okay, so the problem on the exam, I give you 4 compounds and I ask you to rank them in terms of boiling point. And I don't tell you what the boiling points are, but I mean, it's a take home. So I suppose you could figure them out if you could look them up if you wanted to, but it would be hard because I don't give you the names, but whatever. I don't expect you to do that. I don't think you need to do that. In fact, I would rather you didn't do that, but I'm sure people will do that to check on their answers. But what I'm saying is that with thinking about hydrogen bonding and thinking about molar mass, and that the role of dipole forces, that there is a role for that something with a dipole will boil higher than something without a dipole if it has around the same molar mass. Those type of things are what you need to do to reason through that problem on the test. It's similar to the graded assignment that I just gave, which I'm going to post the solutions to that. So anyway, I just kind of wanted to give you a little more on that, so you have a little, more experience with thinking about things like that. Because I mean, in the past, I've seen students say, oh, that one has a 59 grams per mole. It's compared to the one with 58, it's going to have much greater dispersion forces. I mean, that's just not true. The difference in dispersion forces of a few grams per mole doesn't really mean much. And hydrogen bonding, though, I mean, you can have a very low molar mass, and like that example I gave with the HCl and the HBr, and then HF, which is the smallest molecule of all, but it was able to form hydrogen bonds and had much higher boiling point. So it should be okay. You should be able to reason it out and explain it. And the most important thing is the explanation, So I just wanted to tell you about that. Okay. That's it. That's all I have to tell you. So, all right. Bye. I'm going to be sending that academic integrity. If I send it to you and you did it already, just do it again. And I don't know.
Can I just ask you a quick question on like the lab?
Sorry.
Can I ask you a quick question of
Yeah,
the lab?
I'm sure.
Okay, so for number 7 on the lab, like the questions, what are we supposed to be doing? Like, are we supposed to be like?
Well, I think I'd like to talk to you about that, but I have to get the lab handout out and I have to look at it. I don't know, remember what number 7 is offhand. So we can do that in a bit. Let me see if I can find it. Yeah. That's a limiting reactant problem.
Okay, so we're just supposed. I'm supposed to like just do the whole problem.
Right. You're supposed to do that problem, yeah.
Okay.
So basically what you need to do there is figure out the moles you have of each. Let me write that down. Hold on. Let me share the screen here with you. Where is it? Oh, here. Okay. So, you have a reaction.
Yeah.
So what you need to do is take the 23 grams and convert it to moles. And here you need to take the 10 grams and convert it to moles. After you do that, you have to look at the ratio of the moles that you have and see if it reflects the stoichiometric ratio. It won't, because this is a limiting reactant problem. So what you're going to have to do is you're going to have to look at this number of moles here for the iron oxide and say, do I have twice as many moles of aluminum as iron oxide? Just the way we did when we were figuring out if the copper sulfate or the potassium oxalate was the limiting reactant. So did you figure out the moles here yet?
No, I wasn't sure if I was supposed to like do the whole problem or.
Yeah, you're supposed to do the whole problem.
Okay.
So you have to figure out, do you have twice as many moles of the aluminum as you have of the iron oxide? If you have more than that, that means this is the limiting reagent. If you have less than that, it means this is the limiting reagent. And then you use the moles of the limiting reagent to calculate the moles of the product. And when you do that, that is called the theoretical yield. You have a question, DeLon?
Yeah, so for example, for the iron the iron with the oxygen, you would do the 23 divided by the molar mass given.
Yep.
Okay, I just wanted to make sure about that because
It's
sometimes
23.0. grams, you basically 159.7 grams.
Over 1 mole.
Well, no, the mole is on top. Grams is on the bottom because you want these I can't, it's not showing my writing. Grams cancel, see? So that's how you'll get moles. It's not Fe, it's Fe2O3. Okay. So what happens when you do that? What is that? 23 divided by 159.7. It should be 0.7, but I'm having trouble writing down here.
I got like 0.14.
Yeah, 3 sig figs. So let's keep it to 3 sig figs.
Oh, 145.
Okay, I thought it was 0.144, but no, it's 144.
So we wouldn't round there.
Well, I don't know. I did 23 divided by 159.7. I got 0.14402. So it's 0.144 at 3 sig figs. Anyway, that's detail. Doesn't matter. 10 divided by, now aluminum. God, I have the wrong molar mass of aluminum. Can you believe that? Oh my God. Well, I guess it's all right. Oh, sorry, it's 26.98. So it is 27. Good. So this comes out to 0.370. So now you have to look at this and say, okay, do I have more than double the amount of it? Do I have twice as much aluminum? Do I have more than twice as much, or do I have less than twice as much as the Fe2O3?
More than twice.
Yeah, because 2 times 0.144 is 0.288, right?
Yeah.
So that makes what the limiting reagent? If you have more than twice as much of this, then which one is going to run out first?
The Fe.
That's right. So this is the limiting reagent. And then it's just a stoichiometry problem. Figure out how much product, what is the theoretical yield of iron? So how much of this will you end up with? When you get that number in grams, that's the theoretical yield. So this theoretical yield is the grams of iron at the end when you use the limiting reactant to solve that. Yeah. And then it says if you actually get this many grams, what is the percent yield? So then you have to find the experimental over the theoretical times 100, and that's what we call the percent yield. Okay?
Okay.
Well, that's how you do that problem.
Also, I had one more question on like number 2. I double checked like the video, and like all the crystals were blue.
I know, but sometimes you see some white streaks in there.
Okay.
I'm not saying every time.
Okay. I was like really confused. I kept on rewatching the videos. Like, were there white crystals?
Well, you know, all I'm saying is that sometimes in the lab, believe it or not, you see something that's not blue in there. And I'm asking, what could that be?
Okay.
Mhm. Yeah. You're welcome. Good. Any other questions?
Yeah, I have a question. So, you were explaining the boiling point and which one can form hydrogen bonds and the molar mass, and yeah, that was for the boiling point. But I have a question. What if it's, I mean, it would be the same thing if it was for heat of vaporization.
The heat of vaporization.
Yeah. So it depends on if the The
Heat of
molecule,
vaporization and boiling point kind of go together. The higher the boiling point, the higher the heat of
the
vapor.
heat.
Yes.
Okay.
Vapor pressure is the opposite. The higher the boiling point, the lower the vapor pressure at room temperature, because the boiling point, that's the temperature when the vapor pressure above a liquid gets to equal atmospheric pressure. The vapor pressure is high when there are very few intermolecular forces. So something with a higher vapor pressure will boil at a lower temperature because it will reach atmospheric pressure at a lower temperature because it has weak intermolecular forces. So yeah, that's that.
Yeah. Thank you.
Did you see the video on surface tension too? Because I do have a couple of questions that I take out of the videos because I didn't
Oh.
go to class. Yeah, well, you'll look at the video when you need to. So that's why I give you plenty of time to do this quiz. So it's not going to be due until the following Monday.
All right. Thank you. Have a good one.
Bye. Delon, you have another question?
Oh no, I just want to make sure I didn't miss anything.